So in this video, we're going to discuss aldehydes and ketones. We're going to name them, we're going to talk about their physical properties, and we're going to talk about their reactivity. So there's two ways that aldehydes and ketones generally react. And so we'll focus on those two separate ways in separate videos, but we'll talk about what they are in this one. So aldehydes and ketones are different than carboxylic acids and their derivatives because we have our R group here, our carbonyl, so there's your acyl group in general, and then you can use Z because that's kind of what we've been using. Z can either be another R group, so this can be another R group. It can be aryl, it can be alkyl, but it's basically another sort of like rest of molecule, right? Or, so that would be if you have a ketone, or it can be a hydrogen, and that would be an aldehyde. So you have to think a little bit about the difference between these and the carboxylic acids with their derivatives. With aldehydes and ketones, we have carbonyl compounds where Z cannot be substituted by a nucleophile. So these do not undergo nucleophilic acyl substitution reactions. But we can use the carbonyl as an electrophile and we can add to it. So these will undergo nucleophilic acyl addition reactions, and that's it's different, right, than a substitution. So if you think about it, if you have an aldehyde, your leaving group is going to be H minus, right? So if we think about for aldehydes, the potential leaving group would have to be the hydride anion. The hydride anion, so hydrogen, right, H2, has a pKa somewhere around 40, which is pretty weakly acidic, right? It's not even an acid, right? Remember, the lower the pKa, the more acidic it is. So we're talking like, acetic acid is somewhere around 4 or like 4.5, right? So the pKa of H2, right, that would be the conjugate acid of the hydride anion, would be like 40-ish. So what that means is the hydride anion is way too basic. So this is way too basic to leave on its own. So the pKa of its conjugate acid is somewhere around 40. Right? If we have a ketone, we can think about it the same way. So the potential leaving group would have to be R minus. Also too basic to leave, right? You'd have a carbanion. So also too basic to leave. So the pKa of the alkane, so be like methane or ethane or whatever, right? Somewhere around 50 or 60. So not even an acid, right? So meaning R minus and H minus are way too strong of a base to leave. Remember, the weaker the base, the better the leaving group. So we have to do addition reactions with these instead. It means that you can still add to the carbonyl, but Z is not going to take off. So before we start any of the reactivity stuff, let's get through the nomenclature. How do we name these things? So just like everything else, we have a common method and we have a systematic or an IUPAC method. For aldehydes, the IUPAC method is where we're going to drop the E of the parent hydrocarbon and just add al. So IUPAC, you're going to drop the E on the name of the parent hydrocarbon. And you're going to add a new suffix, al, for aldehyde. With common nomenclature, if you have less than or equal to 6 carbons, so just like with carboxylic acids, we're going to use the common nomenclature from carboxylic acid naming. You're going to drop the ic acid and you're just going to add the word aldehyde. So for common nomenclature, for less than or equal to 6 carbons, you're going to use carboxylic acid nomenclature. And you're going to drop ic acid and you're going to add the word aldehyde. So let's do just a couple of examples. I could take something little, just 2 carbons. So there's that Z is an H, right? It's a hydrogen for an aldehyde. If I use IUPAC nomenclature, I'm going to drop the E from the parent hydrocarbon. The parent hydrocarbon for something with 2 carbons would be ethane, right? We're going to drop the E from ethane and we're going to add al. So this just becomes ethanal. Al means aldehyde, just like Ol means alcohol, right? For common nomenclature, that would have been acetic acid. We're going to drop the ic acid and add aldehyde. So this becomes acetaldehyde. This is the stuff of hangovers. So when ethanol is oxidized, the first step is the aldehyde. This is the stuff that sucks, acetaldehyde. Another example, if we have, say, a substituent on our aldehyde, so we could have something like put a hydroxyl group there, and then our aldehyde piece of functionality. So again, just like every other carbonyl compound, that's going to be carbon number 1, right? So the carbonyl carbon, which means that on carbon number 2, we have a hydroxyl group, but we're going to call it hydroxy for naming. So we have 2 dash hydroxy, and then we have 1, 2, 3, 4 carbons. That would have been butane, but we're going to drop the E and put Al. So it'll be butanal. With common nomenclature, that would have been butyric acid with a hydroxy group on the alpha carbon. So we say we have alpha dash hydroxy. And instead of butyric acid, We drop the ic acid and add aldehyde, so this becomes butyraldehyde. With ketones, for IUPAC nomenclature, we're going to drop the E from the parent hydrocarbon and we're going to add one. So one will be the suffix for the ketone. IUPAC is going to use numbers to indicate the carbonyl placement. So to be a ketone, you need an R group on either side of the carbonyl, right? So it's no longer carbon number 1 necessarily, but we're going to give priority to the carbonyl carbon. So that means you're going to give it the lowest possible number, and your substituents will be named accordingly after that. So we're going to use numbers to indicate the carbonyl placement. Except for really little ketones, we don't really use common nomenclature very much for ketones. We have something else, though. We have something called derived nomenclature. It's just a little different. It's kind of reminiscent of ethers. So like naming ethers, you can name a ketone as a ketone. So you're going to name the alkyl groups. They can be the same or they can be different. So on either side of the carbonyl, you'll have an R group, right? You're going to name those in alphabetical order. And you're going to follow it by the name of the functional group. In this case, it would be a ketone. You know how you can have like an ethyl methyl ether, you can have an ethyl methyl ketone. So, for example, we could have something, here's one I'll show you where there is a common name for this. It's small enough and quite common, such that we actually do have a common name. It is pretty rare that you will find a common name on a ketone. IUPAC and derived is usually where it's at. But this, the common name for this is acetone. So there are 3 carbons. However, if you look at the methyl group on the right as just the R group that makes it a ketone, then this is sort of a derivative of acetic acid, even though it's not a carboxylic acid derivative. And it's so common, we actually just call this acetone. But the IUPAC nomenclature would indicate that this is a derivative of propane, right? And you have to tell somebody where the carbonyl is. I mean, obviously, it's got to be on the middle carbon. Otherwise, you wouldn't have a ketone. You would have an aldehyde. But we tell somebody that that carbonyl is on carbon number 2. So 2 dash, that 2 means that the carbonyl is on the second carbon. So if I had 4 carbons, you'd have to let somebody know which carbon that thing was on, or 5 carbons or whatever. For derived nomenclature, we basically have 2 methyl groups. So that's dimethyl ketone. I could have something like, I guess, I'm going to do one more. Something like that, where there isn't going to be any common name for this. We don't usually use common names for ketones. We use IUPAC or derived. The derived, again, is pretty reminiscent of nomenclature for ethers, where you name the alkyl groups in alphabetical order and you follow it up with just the name of the functional group. In this case, it would be a ketone. With IUPAC nomenclature, you need to tell somebody which carbon the carbonyl group is on. So we can number these together. If we go left to right, so obviously you're staring at this and you can see that the carbonyl is going to be on the lower numbered carbon if we go from left to right. You can count from right to left, but you can see that that piece of functionality is closer to the left-hand side. So to save time, I'm just going to number this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So what I have here is 4 dash, and then the prefix for 10 is deca. So this would be decane, but it's decanone instead. What that tells somebody is that we have a 10 carbon molecule. Our longest continuous chain has 10 carbons, and on the 4th carbon we have our carbonyl, and so this ON tells us it's a ketone. If I wanted to name this using derived nomenclature, I would take the alkyl groups on either side of the carbonyl. So in that case, I would have, this would be one alkyl group. So that's a propyl group. And then over here, I have 1, 2, 3, 4, 5, 6. So this is a propyl group. And this is a hexyl group. So you would name this just like if you were naming an ether. Hexyl comes before propyl. So we have hexyl, propyl, ketone. You can have a ring. So unlike with an aldehyde where there isn't an R group, it's just a hydrogen, I could have a cyclic ketone. There's no common name for this. There's no derived name for this because the alkyl groups are the same on either side, but they're connected. So there's really one name for this, and it's cyclohexanone. So instead of cyclohexane, we have cyclohexanone. Okay, so let's talk a little bit about the physical properties of these things. Physical properties, and I guess we'll tag on reactivity toward the end. We have, once again, just like with our carboxylic acids and their derivatives, we have some polarity here. So I'm going to do this. It could be an R or it could be an H. Instead of putting a Z there, I'm going to do that. So that carbonyl is polar. So in other words, I've got a partial negative charge on the oxygen, partial positive charge on the carbon. So there's polarity. Associated with the carbonyl. Oxygen is more electronegative, right, than carbon. So the oxygen has a greater share of the double bond electrons, right, the electrons that are involved in the double bond. Aldehydes, we have to kind of talk about them just a little bit separately here. Aldehydes have a greater partial positive charge on the carbon than ketones do, because an alkyl group does a better job supporting the positive charge. Remember when we talked about intermolecular forces in general chemistry, the more mass you have associated with a species, the greater the dispersion forces. So just like more alkyl groups on a nitrogen will make that nitrogen containing molecule more basic, right? It helps to localize the electrons on the nitrogen, right? If we're talking a piece of polarity in this molecule would be the carbonyl functionality. There's a dipole moment going in this direction, right? If R is attached instead of H, right, then that R group, that alkyl group, does a better job supporting, through an inductive effect, it does a better job supporting that partial positive charge than a hydrogen would, right? So think again, dispersion forces. So aldehydes in general, right? Of course, it kind of depends on the rest of the structure. They have a greater partial positive charge on the carbon of the carbonyl. So all other things equal, if you have an aldehyde or a ketone and that R on the left-hand side is going to be the same, so we're comparing apples to apples here. If I have an aldehyde and over on the right it's just a hydrogen, then the partial charge on the carbonyl carbon is going to be greater than if I had a ketone. So what does that mean? It means that these are going to be more reactive toward nucleophilic attack. So if you're just comparing, an aldehyde to a ketone, and the R group on the left-hand side is, say, just a methyl, right? And the ketone, say you have acetone, right? And you have like acetaldehyde, right? So we have a methyl group on the left for both. Acetaldehyde just has a hydrogen on the right, and acetone has a methyl group on the right. Then acetaldehyde is going to be more reactive toward nucleophilic attack because the carbon is more electropositive. It's more electrophilic, right? It's more deficient in electrons. The other thing that we have to think about too are the sterics. If you have a ketone, sterics are going to contribute to the greater reactivity of the aldehyde. So the carbonyl carbon is going to be more accessible in an aldehyde. So we're making a little list here. We could say sterics, meaning things in the way, right? Sterics in ketones can make the carbonyl carbon less accessible. if I have two T-butyl groups on either side of that carbonyl, even though it's sp2 hybridized, right? Compare that to on one side you just have a hydrogen. I mean, you know, it's easier to get at that carbon when there's less in the way. So if you wanted to make a little list in terms of reactivity between, say, aldehydes and ketones, we could take the smallest aldehyde we have, which is just one carbon, that's formaldehyde. So we could have just, this is formaldehyde. It's the smallest, right? It's going to be, if aldehydes are more reactive than ketones in general, then this being the smallest aldehyde is going to be even more reactive than any other aldehyde, which will be even more reactive than any ketone. So this, in other words, is our most reactive. It's the smallest, and the partial positive charge on the carbon is the least supported in this particular molecule. That is the most reactive. Regular aldehyde over here. This is just where R is any alkyl or aryl group. And then a ketone, because the partial positive charge on the carbon is better supported through an inductive effect when we have an alkyl group attached instead of a hydrogen. So this will be the least reactive. But all of them are reactive toward nucleophilic acyl addition reactions. So a nucleophile, in other words, can attack the carbonyl carbon in all of those cases. The formaldehyde is going to be the most reactive. The ketone will be the least reactive. So if you're talking, now we're going to take aldehydes out of the mix and you want to compare ketones, we use sterics again. For the same reason, ketones that have smaller alkyl groups bonded to the carbonyl carbon are going to be more reactive than those with larger ones, right? So less stuff in the way. So for example, I could take acetone, with just methyl groups. This will be our most reactive ketone. And I'm going to start bulking up the alkyl groups, the R groups on either side of the carbonyl. We'll keep the methyl group on this side. And over here on the right, I'll put an isopropyl group. And then in this one over here, we'll put isopropyl groups on both sides. We are increasing the sterics as we bulk up the groups that are around the carbonyl, making it less accessible for the nucleophile. So of these three, this would be the least reactive. So remember, it's sp2 hybridized. The carbon is sp2 hybridized. So this is trigonal planar in all cases. However, if you're comparing across the board there, those ketones, then the acetone carbonyl is going to be far more accessible than the diisopropyl ketone. We want to compare the reactivities of aldehydes and ketones with other carbonyl compounds. Again, our most reactive. So we'll compare reactivity to other carbonyl compounds, like our carboxylic acids and their derivatives. We have our acyl chlorides. These will be our most reactive. Now remember, these are going to undergo nucleophilic substitution reactions, right? Because the chloride is a good leaving group. But in terms of reactivity, in terms of the carbonyl, not saying we're doing, substitutions or additions, we're just comparing all carbonyl compounds. Carboxylic acids and their derivatives undergo nucleophilic acyl substitution reactions, while aldehydes and ketones undergo nucleophilic acyl addition reactions. So we have our acyl chloride. We can put in the acid anhydride. Going to be more reactive than an aldehyde. Which will be more reactive than a ketone. Which will be more reactive than an ester, which is kind of the same as a carboxylic acid. Abbreviate that because it's too long, take up too much space. Which will be more reactive than an amide. Remember, those were pretty sluggish. Our least reactive, these aren't really going to be attacked by a nucleophile, right, because they're already basic, will be our carboxylate anion. Oops. I believe we also discussed nitriles. Nitriles are going to be down there, less reactive than an amide as well. So this is least reactive. So in terms of the two ways that in this class we're going to discuss aldehydes and ketones reacting, the first way we've been saying all along here is these can undergo nucleophilic acyl addition reactions, not substitution reactions. Again, acyl refers to the R and then the carbonyl, right? These are addition reactions. A nucleophile can add to the carbonyl carbon, but it's not going to, there's no leaving group. So it's not going to be a substitution. We're not putting the nucleophile in place of another group. So it's an addition reaction. There is no leaving group. So in general, what that means is we could have our ketone or our aldehyde. We could have it attacked by a nucleophile. And we find that the nucleophile has added right? We have our tetrahedral intermediate, just like we did before. And we work this up with some acid and protonate the oxygen. So we have effectively added a nucleophile to the carbonyl carbon, and we have then protonated the negatively charged oxygen to create an alcohol, depending on what the nucleophile is. The other way, and that'll be a separate video, we have a whole bunch of different nucleophiles. So for example, our different types of nucleophiles can be carbon containing, we can do a Grignard reaction, or we could react, I should say, an aldehyde or a ketone with a Grignard reagent. We could add cyanide. We could add, let's see, we could deprotonate a terminal alkyne. Remember way back when we did alkenes and alkynes, we said that terminal alkynes can be really weakly acidic, and with a strong enough base, you can deprotonate the alkyne to make a carbanion. It's a good way to make a new carbon-carbon bond. That could be a nucleophile. So any carbon-containing nucleophile, we could have hydrogen-containing nucleophiles. We, believe it or not, actually already talked about this a little bit. We call these reductions or redox reactions with a source of the hydride anion. So remember way back when we did alcohols and we oxidized an alcohol under anhydrous conditions with pyridinium chlorochromate, right, and methylene chloride, so that we would stop the primary alcohol from going all the way up to the carboxylic acid. So we stopped at the aldehyde with that, right? You can take an aldehyde then, and you can allow it to be reduced in the presence of a hydrogen-containing nucleophile. So in Gen Chem, we talk about redox reactions as a gain or a loss of electrons. And it's the same in organic chemistry. It's just in organic chemistry, we're talking about changing up some functionality. And it's easier for us to see an oxidation reaction because we're increasing the number of carbon-oxygen bonds, decreasing the number of carbon-hydrogen bonds. In a reduction, we're going to be decreasing the number of carbon-oxygen bonds and increasing the number of carbon-hydrogen bonds. And the way that we do that is we add a source of H-, or in other words, a hydrogen-containing nucleophile. So in organic chemistry, we're still talking about nucleophiles and electrophiles when we talk about redox reactions. In Gen Chem, it's a little different. It's like, okay, you know, did the silver take on a positive charge, or did the silver ion go neutral? It's a little easier to see. But in organic chemistry, we have redox reactions. And a reduction would be allowing some, you know, piece of functionality to react with a molecule that has a hydrogen-containing nucleophile. So something like sodium borohydride or lithium aluminum hydride, or, you know, something like that. We are taking a hydrogen-containing nucleophile. We have nitrogen-containing nucleophiles. So amines or ammonia. Those are the ones that we talked about anyways. Obviously, there are lots of others. Oxygen-containing nucleophiles is where we're going to introduce some new functionality. So alcohols, the hydroxide anion, water, right? So oxygen-containing nucleophiles. We'll do chemistry with all of those. The second way, and that will be, again, this second way will be its own video, a third video. This will be reactions specifically at the alpha carbon So in other words, we're going to do what's called enolate chemistry. In your textbook, I think this has its own chapter, comes after the aldehyde ketone chapter, I believe, or maybe it's a couple of chapters ahead. So I'm going to introduce something called the enolate ion. And what we get to see is an aldehyde or a ketone can react with another aldehyde or a ketone if we deprotonate the alpha carbon of one of them, create an enolate ion, which now will act as a nucleophile, attacking the other aldehyde or ketone. What am I talking about? So I'm talking about the special case where the hydrogen on the alpha carbon, otherwise sometimes known as the alpha hydrogen, has a particular acidity to it. I'm exaggerating these bonds so that you can see what I'm talking about. I'm going to take a base, and we're just doing this generically right now. We're going to deprotonate the alpha carbon, or in other words, we're going to remove the alpha hydrogen. These electrons are going to go on to the alpha carbon to make a carbanion. Normally, you wouldn't think that you could do this, right? You would be like, wait a second, I'm not going to just go out and say deprotonate ethane, right? Because what do? You get a lone pair of electrons localized on that carbon, right? So this is an sp3 hybridized carbon that we are going to deprotonate. You don't expect that you normally can do that with a regular old alkane because you would be localizing the electron density on that carbon. It has nowhere to go. But check out how you have an electron withdrawing group nearby. We have our alpha carbon attached to a carbonyl. So what I can do is I can delocalize these electrons up into the more electronegative atom, that is oxygen. And I get what's called an enolate ion. So normally I don't stick these dots on here, but this thing right here is our enolate ion. And that can behave like a nucleophile. When the carbonyl reforms, so I could send these electrons back down, reform the pi bond, these electrons can go off and attack some electrophile. We can actually attack another aldehyde or a ketone. What you're actually doing is forming a bond between the alpha carbon and the electrophile. So if you want to view it, sometimes it's easier to view it as we're using these electrons are on that carbon, right? So we have our resonance contributing carbanion over there. We'll have a whole section just on enolate ion chemistry. There's a few named reactions that I'd like to share with you, and those will be the two different ways that we are going to react aldehydes and ketones. We are going to do nucleophilic acyl addition reactions, and we're going to do reactions at the alpha carbon.